Russia's war in Ukraine is increasingly blowing up in Moscow. This Ukrainian drone attack Sunday night, bringing Russia's war hundreds of miles away into the heart of its own capital, shocking citizens.
In the past decade, drones, often referred to as unmanned aerial vehicles, have undergone a major shift from an innocent children's toy to modern instruments of war. Destructive drone swarms have popped up in conflicts all across the globe, most notably in the Middle East and the recent Ukrainian conflict. Forbes magazine even goes as far as to say, drone and counter-drone technologies have become critical tools on the modern battlefield, with the outcome of conflicts increasingly hinging on the superiority of these systems. As the drone playing field becomes increasingly relevant and crucial to modern warfare, the Department of Defense is determined to not be left behind. Investing millions this past year in drone technology, the United States is looking to come up with increasingly clever ways to advance in the realm of drones, including 3D printing parts. Drones are beneficial to the warfighter in many ways. They can gather valuable intelligence, conduct reconnaissance missions, and track enemy movements effectively. This enhances situational awareness and allows for a safer deployment. By designing drone parts to be 3D printed, warfighters can adjust model flaws quickly and reprint on-site. It allows for the drones to be lightweight and easily repairable. Repairing, updating, or receiving drones no longer requires shipping time and costs, but can now be made in-house. Engineers can send their designs to the warfighter in minutes. Yaw's at-home drone attempts to play into this idea and adds a unique twist, adding flexible sensors and a custom mobile application for data recollection.
This is our final design solution. It fulfills all of the requirements dictated by our design requirements. Most importantly, that it needs to be easily 3D printed, easily assembled, needs to house all of the required components for our design, which includes the obviously SpeedyBee controller, the Raspberry Pi, sensors, voltage regulator, batteries, etc. Moreover, the design is stiff, rigid, and lightweight, and actually flies. So the first design requirement that we looked at that was most important was being able to 3D print this design for mass production. And a large constraint of 3D printers is the surface area of the printer bed. That is the maximum area we can print. And in this design, you can see the top piece is our largest component. So it's very important that that top piece was within the area required by our 3D printer, which was 220 by 220 millimeters. You can see that part right here, and the design is made to be 180 by 180 with about 13 millimeters extra, so about 203 millimeters by 203 millimeters each way to ensure that it can be easily 3D printed. Now, this design was actually our third iteration. Our first iteration looked like this. It has the same dimensions of about 200 by 200 to stay within the printer's area. However, this design was not so great because the propellers were directly above both the top portion and the legs below, as you can see here. This would have led to poor flying performance, as well as the battery being placed very high up on the drone would have led to it being top heavy, further decreasing the flight performance of the drone. In our second design iteration, we resolved those issues by moving the blades farther away and by rearranging the components within the drone to utilize both the top and the bottom portions of the drone interior to mount components. As you can see here, we were only utilizing the lower half the bottom portion to house the components. So housing components on the roof this way greatly reduced the area and enabled us to reduce the surface area directly below the propeller blades. This design was built, created, and tested, and during flight testing it was determined that the motors were causing far too much vibration on the motor arms, which you can see here, which are too thin and too small in general to handle the forces. So in our final design, we added diagonal bracing both in the vertical direction and in the horizontal direction, which completely negated the vibrations of the motor and enabled this drone to successfully fly. And we're very happy with this final drone design because it's lightweight, it is very stiff and rigid, and is able to house all of the necessary components we need for our design requirements. This design could be improved in the future, however, by increasing the strength of the legs. They took a lot of damage on landings, let's say, but otherwise we were very happy with our drone design in the end, and that is how we came up with our final design. Thank you.
To best test each drone, both drones were selected different initial flight days based on the experienced pilot's availability and the weather for their location during that time. The first test flight is the one being shown currently. This was taken on November 27th and was piloted by teammate Mr. Shangle. This was conducted in the city, so different factors do play a part, one of which being wind and areas that the drone is able to fly, open areas the drone is able to fly. The drone had a successful takeoff and is able to maintain that stability in air. Unfortunately, wind does start playing a factor towards the end of the video. This does result in a slight crash, but it is suspected without the wind or a lower risk of wind that the drone would be able to meet this 2 to 5 minute constraint. Next video will be our second flight. This test flight is from the Clemson drone that is piloted by an experienced pilot. Unfortunately, we were not able to achieve successful takeoff in this. That is because motor 2 is currently receiving the most power. So once the voltage is able to be regulated amongst all motors, a more even flight and successful takeoff will be occurred and will be updated upon. Here is the data the drone collects during flight. The data is compared to the actual versus taken and inside versus outside, as well as with the battery attached and without. It was important to get the data with the battery attached and without to compare because, as one can see, the battery does play an effect in the heat. This would be able to be solved with a redesign that would be able to be continued if the project was furthered and is identified as a weakness.
Throughout the project, there have been strengths and weaknesses identified that can be built upon and improved upon for future modifications of this drone. Some of the strengths are the modular and cheap design of the drone, allowing for multiple drones to be constructed at a lower cost, in which multiple drones will then be operational. Additionally, the modifications to this drone are very quick, allowing for at-home and in-the-field modifications. So one mission can be run and then quickly modify the drone after that mission is complete to send out for a completely separate, or to expand upon the data collected within the first mission. There's also a successful proof of concept, and it is sturdy, allowing for multiple flights to occur before the battery needs to be recharged. However, there have been weaknesses found with the lightweight aspect of the drone that can be heavily affected by wind, so it does require a skilled pilot to fly it during these missions, and the heat from the battery interferes with the temperature and humidity sensor, causing fluctuating readings from those sensors, and there is a cheap gas sensor to detect hazardous and toxic gas, which can cause misreads during the mission itself.